Hi, it's Gary. Welcome to today's video. Well, why does the Earth have life but our neighbouring planet Mars? It's devoid of life and it's got very little atmosphere. Really, a little bit like any party that I would host. Well, it's down to the magnetic field that surrounds the Earth. This field, it's known as the magnetosphere, and it protects our planet from harmful radiation and particles. This magnetic field is created by the planet itself, and it provides us with a useful navigation tool as well as protecting the planet. The Earth, it's made up of four main layers. At the centre, we've got the inner core. This, it's made up of solid iron with some nickel in the mix. It's about 1,200 kilometres thick, and it's as hot as the surface of the sun. So I would think you'd get quite a quick sunburn there, wouldn't you? Surrounding this inner core is, well, strangely enough, the outer core. I know that's some nifty naming, isn't it? The outer core, it's also made up of iron and nickel, but this, it's now molten and it flows via convection. We'll come back to this soon. The outer core is about 2,250 kilometres thick. Next, we've got the mantle. It's about 2,900 kilometres thick, and this, it's made up of molten rock. Then the final layer, that's the crust. This, it varies in thickness from just a few kilometres under the oceans to about 31 kilometres above land. This, best way to think about it, is the solid rock on which we walk on. Coming back to the outer core, this is where the magnetic field is generated. With this mix of iron and nickel being molten, it's able to flow. The heat coming from the inner core triggers convection currents in this molten metal. This convection drives the flow of the molten metal. As the metal flows, it generates an electric current. And these currents, they're hundreds of miles wide and they move at many thousands of miles per hour. This process, it's called the geodynamo. The electric current then drives the magnetic field that surrounds the planet. The magnetic field, it forms two poles, which we call the North Pole and the South Pole. Imagine this as if there was a large bar magnet going through the Earth. We've got different poles on different ends. These magnetic poles, they don't coincide with the poles around which the planet spins. Instead, they're roughly 11 degrees off from it. And the magnetic poles, they do move around a bit. Over small timescales, we're talking years here, the movement is quite small. But over geologic timescales, thousands, millions of years, this can actually make quite a difference. Another thing to be aware of, roughly every 200 to 300,000 years, the poles, they switch places. And we know this by looking at ancient rocks. These ancient rocks, they contain minerals that are affected by the magnetic field. And these, they record enough information that scientists are able to use them to determine a lot of details about the ancient magnetic fields. During a pole reversal, the magnetic field, it does weaken, but it doesn't completely disappear. We took a bit of a tangent there. Let's get back to the outer core. The convection currents in that outer core, they do change over time, albeit it's quite slow. As these change, the magnetic field does weaken or strengthen. At the moment, the magnetic field is weakening, and it's about 10 to 15% less than it was 200 years ago. So now we know how that field is generated. Let's take a look at a couple of things that it does for us. The first one, it's the easy one. It lets compasses work. And for the younger generation, a compass is a tool that you used to aid with navigation before GPS was available. Please drop a comment down below. Would you like a separate video about how compasses work? The magnetic field, it drops into the Earth at the magnetic North Pole. A compass, it's actually got a little small metal bar inside it, which is attracted to that North Pole. So the bar, it's normally got a little white bit of paint on the end, which is slightly luminescent. That always points to the magnetic North Pole. The second way the magnetic field benefits us is through the magnetosphere. As we started the video, it can be thought of as a protective shield that surrounds the Earth. This shield, it deflects the solar wind. Now, that's a stream of charged particles that the sun sends out. The solar wind, it also has a magnetic field. The magnetosphere, it deflects these particles so the solar wind flows around the bubble rather than over the Earth. It also deflects cosmic rays. These are high-energy rays and particles from outside of the solar system that are coming towards the planet as well. The solar wind, it does have an impact on the magnetosphere. Because the Earth, well, it's more or less round, we would expect the field to be the same shape. It isn't. It's compressed by the solar wind on the side that's facing the sun. The magnetosphere on the sun side extends roughly 3 Earth radii from the planet. On the back side of the planet, the one that's facing away from the sun, the solar wind, it still acts on the magnetosphere, drawing it out into a tail. On the side away from the sun, the magnetosphere extends for about 200 Earth radii. The magnetosphere, it's not a perfect defence. The solar wind, it's still able to open cracks in the defence, and it does let some atoms through. These cracks, they are quickly closed, so the amount of atoms getting through, they don't pose a danger. And the added benefit of this, these atoms are what drive the aurora. The atoms, they get trapped in the currents where they're drawn together at the poles. Here, they interact with the atmosphere and they generate those gorgeous auroras that we can see. But we still haven't talked about what the magnetosphere is protecting us from. Without the magnetosphere, the solar wind would not be deflected from the planet. This means the solar wind, it would hit us full on and it would strip away the atmosphere. This is what they think happened on Mars. Without the atmosphere, there'd be no air to breathe. Temperatures would drop. Life just couldn't exist. The other benefit is more related to modern technology. Without the magnetosphere, we would be at the mercy of the high-energy particles that are flowing towards us, and they would severely impact electronic devices. A couple of examples. The first one, this is from 1859. This is actually the big one. In this year, there was a large coronal mass ejection from the sun, and the Earth was directly in its path. The energy in this, it was enough to make it through the magnetosphere. It was strong enough to create electric currents in telegraph wires. This, it's known as the Carrington event. Just imagine the next time this happens, and it will happen again. We're now so dependent on electronic devices. An event like this would very likely fry most of our electronics. It's going to impact every device. Chances are it'll impact virtually all infrastructure. It's likely to cause global chaos. Our second example, a bit more recent, 2003. There was a solar storm and it sent more than the usual amount of particles towards us. Some of these, they were able to get through the magnetosphere and they impacted satellites, spacecraft and navigation systems. About 1/3 of all NASA satellites were impacted by this. Imagine the satellites that we use for GPS, for communication. What if they were all to suddenly stop working? All this means that the magnetosphere, it's that invisible protector that we're just not aware of. It's part of the reason we're actually able to be here. It's part of the reason why you're able to watch this video. This was interesting. I liked this one. I really enjoyed researching this. What are your thoughts? Do you know much more about the magnetosphere? I'd love to get people's input. Please drop a comment down below. Let's kickstart the conversation. Please hit that thumbs up button. Every time you like, every time you comment, it just helps with the YouTube algorithm. If you haven't already, please subscribe to my channel so that you can get new videos as I release them. I'll talk to you again soon.